Hello everyone, this is lecture 4 of ComSci 141, Nondeterministic Finite Automata. In the last video, we discussed regular languages, regular expressions, and how to prove the set equivalence of a DFA's language and the regular language. In our finite automata outline, we are now currently in our third topic. So in today's video, we will discuss nondeterministic finite automata, NFA with epsilon transitions, and epsilon closure. So previously, we said that there are two types of finite automata, and in the previous video, we discussed deterministic finite automata, wherein if you're given an input, one state will transition exactly to one state, so it's deterministic. The other type of finite automata is the non-deterministic finite automata, or NFA, wherein if you're given an input, one state could transition to more than one state. So to see the difference, in the DFA, given that you're in state Q, if you're given input A, you are assured that you will only transition to one state, let's say P. Okay, so it's deterministic. But in the NFA, or non-deterministic finite automata, given that you're in state Q, and on input A, you could transition to multiple states. So Q on A could go to P, Q on A could go to R, Q on A could go to S. Okay, so you're not sure where it would end up. So it's non-deterministic. So in the DFA, it remembers where the control currently is, which is only keeping track of one state. But in the NFA, it has the ability to be in several states at once. Okay, so several states at once, just like this girl here who's doing a acrobatic bridge pose in the Four Corners Monument. So this spot is where the borders of the states of Utah, Colorado, Arizona, and New Mexico intersect, right? So by doing this pose on the Four Corners Monument, this girl is actually in 4 states at once. Okay, so being in multiple states at once is kind of pretty cool. Okay, so let's talk about the 5-tuple notation of the NFA. And more or less, it has the same ingredients as your DFA. So you still have your Q, or the finite set of states, sigma, which is the finite set of input symbols, delta, which is the transition function, Q sub 0, which is the initial state or start state, and F, which is the set of final or accepting states, which is a subset of the set of states. Okay, so it's more or less the same with DFA, but what do you think is different from the DFA out of the 5? So out of the 5, it's the transition function, delta, which is different. Everything else is the same. Because in the DFA, the transition function maps a state and an input symbol to one state. But in the NFA, the transition function maps a state and an input symbol to a set of states. And it could be possibly empty as well, because it's a set. Okay? So in the DFA, you're assured of one state. In the NFA, it could be 0 or more states, which is a set. So formally, the transition function delta maps the set of states Q and cross product that with the set of input symbols sigma, and they map that to set of states Q as well. So state symbol map to state. But in the NFA, we have the transition function mapping as set of states and an input symbol to 2 raised to Q. Now, what is 2 raised to Q? We call this the power set of Q, which is the set of all subsets of Q. Okay? So, what does that look like? So, let's see an example. Let's say that your set of states Q has 3 states, so A, B, and C. So, your 2 raised to Q, which is the power set, will be the following. So, You could have the empty set, okay, taking nothing. You could have the set containing only A, set containing only B, set containing only C, set containing A and B, A and C, B and C, and all three A, B, C. So it's the set of all subsets. Okay, so it's the power set. So that is the difference between the NFA's transition function and the DFA's transition function. The same is true for the extended transition function delta hat. In the DFA, you map a state and a string to one state for the delta hat. And in the NFA, given a state and a string, it could go to a set of states also and possibly empty again. Okay, so the same thing, even with the extended transition function. So formally, the delta hat in the DFA maps Q cross with sigma star, which is a set of strings, to just a set of states. So only one state. But in the NFA, Q and the sigma star is mapped to the power set of Q 2 raised to Q. So just like your transition function. Okay? Now for the acceptance of the string, we start at the start state Q sub 0, and then from one state, we transition on an input symbol. The transitions on an input symbol can be to any set of states. Okay? So if, for example, A transitions to B or C, then we could be at either B or C on that transition. Okay? And we accept the string if any sequence of choices lead to any of the final states. So since we have a lot of possible states that we end up in, as long as one sequence leads to one of the final states, then we accept the string. Okay? So let's see an example. We have a colored board here with red and blue numbers. So the odd numbers 1, 3, 5, 7, 9 are colored blue, and the even numbers 2, 4, 6, 8 are colored red. So they are arranged in a 3 by 3 grid, and our goal is to design an NFA to model moving on this 3 by 3 checkered board. And so we have 9 states here, 1 to 9, and then we have two input symbols. We have the red and blue. So red means that you move to an adjacent red square, and blue means you move to an adjacent blue square. Okay. We start at state 1, and our goal is to end up in state 9. So we start here in 1, and our goal is to end up in 9. And given color transitions like red and blue, can we reach our goal state? Okay, so that is what we'll model. So this will be the transition table for such NFA. So for example, we start at 1, and then our uh, goal state is 9, and then on 1, if you take a red square, that the neighboring red squares are 2 and 4. So we have 2 and 4 here. And then if you want a neighboring blue from 1, you go to 5. And then sa 2 on red, that would be 4 and 6. And then 2 on a blue, that would be 1, 3, and 5. 3 on a red, that would be 2 and 6. 3 on a blue is only 5. And so on. Okay, so last na lang ang 5, for example. 5 on a red would be 2, 4, 6, and 8 because those are the adjacent red squares. And then on a blue, that would be 1, 3, 7, 9. So it could be diagonal, left, right, up, down, as long as it's adjacent. Okay, so yeah, so those are the allowed moves. Okay, so given this, what if our input string was red, blue, blue? Will we reach um, the what do you call this? The goal state. Okay, so let's start at 1 because this is our start state, on red, 1 could go to 2 or 4. So currently, we are now in 2 or in 4. Now, in these states, if we take the next input symbol, which is blue, 2 on a blue will go to 1, 3, or 5. So 1, 3, or 5. But then, ang sa 4 naman, what if you ended up in 4? 4 on a blue goes to 1, 5, and 7. So you go to 1, 5, or 7. So all in all, after taking the second input symbol blue, we could be in states 1, 3, 5, or 7. Okay? So we are in all of those states at once. And then finally, from these states, if we take a blue, so from 1 taking blue, that would only be 5. So here, 3 going on blue is also going to 5. 5 on blue will go to either 1, 3, 7, or 9. And then 7 on blue will also go to 5. Okay? So now, we are currently in either 1, 3, 5, 7, or 9. And since we have finished our input string, and we have arrived at one of the final stage, which is 9, then we will accept this input string RBB. Okay? Because we arrived at one final state after processing the whole string. Okay, so we accept it since the final state is reached, and it's irrelevant that it also ended up in states 1, 3, 5, and 7. So it doesn't matter that it ended up in other non-accepting states. As long as you reach one final state, then you accept the string. Okay, so you can think of it like this. So the NFA is in all of these states in parallel. Okay, so if the DFA only has one control that moves from one state to another, the NFA has multiple controls that are monitored in parallel. So if it branches out to two different states, then you have two controls currently. And then if those two states branch out to, let's say, two more different states, so two each, then you have four controls now in total. Okay, so you can think of it like Naruto's Kage Bunshin technique, where he produces shadow clones. So there's more controls, the more states that are possible to be that you end up in. Okay, so yeah, there are multiple controls in NFA. So let's see more examples. Let's say, given this NFA, can we accept the input 00101? Okay, so we could do it like this. So 0, 0, 1, 0, 1. So that is accepted. Okay, so but if we did it the wrong way, so for example, we could have had it like 0, 0, 1, 0, 1. So it only stays in A, right? Or let's say 0, 0, no. Let's say 0, 0, 1, and then you get stuck because there are no transitions anymore. So it's not accepted, right? But since there is one way for you to get to the final state, which is 0, 0, 1, 0, 1, then it is accepted. Okay? So as long as one path leads to a final state, it's accepted. Let's see one more example. In this NFA, let's get the input 0, 1, 0, 0, 1. So maybe we could do it like this: 0, 1, 0, 0, but then we get stuck there because there's no one transition. So let's try another one. We have 0, 1, 0, 0, 1. Okay, so we have reached a final state, and so this is accepted. So again, because it's NFA, it's non-deterministic, there could be multiple ways that you could control or traverse the NFA, but as long as one of the path leads to a final state, then it is accepted. Okay, so again, the path was 0, 1, 0, 0, 1. So we ended up in the final state C, so that is accepted. Okay, so that is how strings are accepted in the NFA. Now, question. Um, the NFA has a lot of choices for which states to go to. So if one state can transition to multiple possible states, how does the NFA know which state to actually transition to go to the final state to be accepted, right? So the intuition there is that the NFA always guesses right. So it has like a you can think of the NFA as like a fortune teller or something. Like it can guess, like if I take this path, if I take this state, I will end up in the accepting state. Okay, so you can just think of the NFA as having that power that uh, it can guess correctly which state leads to the final state. Okay, so this seems like a good power to have, like, right? So the power of non-determinism, that you can choose the correct path to go to so that you'll be accepted and up from among many possible states, no? With the power of non-determinism, does this make the NFA a more powerful model than the DFA? Because it seems like we have added more capabilities to the NFA, right? So the answer there is, even with the power of non-determinism, the NFA still only accepts the regular languages like the DFA. So in reality, the power of non-determinism is only for convenience, but in fact, it doesn't add more computing power to your finite automaton. So it still only accepts the same set of languages as a DFA. Okay, and as we'll see in the next video, in the next topic, we can convert an NFA to a DFA and vice versa. Okay, so we can say that they are equivalent. Okay, so now we are ready to define the language of the NFA. So the language of the NFA is the set of strings that it accepts. Okay, so and as we said, the string W is accepted by the NFA if delta hat starting from the start state Q sub 0 and processing the string W contains at least one final state. Okay, so the delta hat, take note, is a set of states as well, right? Because it could end up in multiple possible states. But if one of those states is a final state, then you accept the string. So formally, the language of the NFA named A is written as follows. So all strings W such that delta hat Q sub 0 taking W processing W, so this is a set, and you take the intersection with final states is non-empty, meaning there is one final states in delta hat Q sub 0 W. Okay, so that's it. Okay, so that's NFA. Let's now go through um, an extension of NFA, and this is NFA with epsilon transitions, or epsilon NFA. Okay, so what are NFA with epsilon transitions? So it's a finite automaton that allows state-to-state transitions on an empty string input. Okay, so you allow transitions on epsilon, meaning you don't take any input symbol. So you allow the NFA to transition without taking an input symbol, as I mentioned. So what does that look like? So this is an example epsilon NFA. So you'll notice that besides the zeros and one transitions, there are also epsilon transitions. Okay, so there's an epsilon transition from E to B, from E to C, from B to D. Okay, and what this means is from E, you can freely transition to B without taking any input. Okay, so we'll see that in an example later. So the analogy here is something like this. You can think of this map. The states here are islands, okay, and the lines that connect them are bridges. Okay, so the islands are states, the bridges are the transitions, and the directions are the input symbols. So like, so for example, take the bridge labeled 0, take the bridge labeled 1, and so on. Okay, if you are using a DFA, you are traversing this map alone. So you're running alone. Okay, so your goal is to from the start island, your goal is to finish in this island. Okay, you are running alone if you are in the DFA. So if you get lost running around, then well, yeah, you get lost. You're alone. In the NFA, you can think of it as having Naruto's shadow clones, right? So there are multiple clones of you who are possibly running around, and if one of you or your clones reaches the goal state, then you've succeeded. And then in the epsilon NFA, you can think of it as having the power to teleport, okay? Or more precisely, if you have seen Harry Potter, it's like traveling through the flu powder network, right? Because, for example, there's a like portal here, and there's a portal here. Then you can teleport from here to here without going through the bridge, okay? Or from this portal to this portal, you can teleport without crossing any bridges, okay? So that's a free teleport from here to here or any other um, states with a portal if you use epsilon NFA. Okay, so that's your little analogy. Okay, so going back here, um, example, if you have the input 0, 1, from here, from A, you can, on a 0, you go to E, but then since there's no 1 here, but there are epsilon transitions, you can freely transition to either B or C. And then you can get your A here, your 1 to C or to D. You can even transition to D on another epsilon here. But yeah, you can freely transition to another state without taking any input on epsilon transitions. Okay, so for the 5-tuple notation, it's practically the same as your NFA, but the only difference is that the transition function delta now has entries for the transitions on epsilon, because you have to also define the epsilon transitions, right? However, please take note that epsilon is not part of the set of input symbols sigma, because it's not an input symbol, it's an empty string, but it's just a extra extra input that we need to take note of, the epsilon. Okay, so in the NFA, we map the set of states Q and the set of input symbols sigma to the power set 2Q. And in the epsilon NFA, the only difference is that we map Q and sigma together with the empty string. So we just add the empty string together with the input symbols. And we still map that to the power set. Okay, so it's still a set of states, possibly empty. Okay, so let's use our example epsilon NFA again. The transition table would look something like this. So for example, on we have how many states here? 1, 2, 3, 4, 5, 6 states. That's A, B, C, D, E, F. And then for our symbols, we have 0 and 1. And then we have the extra column for epsilon transitions. And then start state is A, final state is D. So on A on 0 goes to E. But take note, it should be in set notation. So you wrap it in curly braces because it's a set of states. So even if there's only one, uh, wrap it in curly braces because it should be a set. Okay, so that's the difference between your DFA and NFA. In the DFA, you're assured of one state. In the NFA, even if it's only one state, it should be in set notation. Okay, so A on 0 is the set containing E. A on 1 goes to set containing B only. A on epsilon, there's no epsilon transition, so that's null, okay, or empty set. B on 0 doesn't go to anywhere, so it's null, also empty. B on 1 goes to C, so it's here. And then B on epsilon goes to D. So we have that here. Okay, and then do the same for the rest. Like for example, sa D, it doesn't have any transitions going anywhere, right? So all the transition function entries here are empty because it doesn't transition anywhere. And then for E, for example, it has two epsilon transitions, so going to B and C. So you have that here as B and C on epsilon from E. Okay, so hopefully that makes sense. Yeah. Okay, so with this new added feature of uh, allowing epsilon transitions, is the epsilon NFA a more powerful model than the NFA? So earlier we said that with the power of non-determinism, the NFA is still has the same computing power as the DFA, but now we have added a more powerful feature which allows us to teleport right from one state to another without processing an input symbol. So that seems like it should add more computing power to our model. However, even with the power of epsilon transitions, epsilon NFA still only accepts regular languages like DFA and NFA. So it only adds convenience with the transitions, but it doesn't really add to the computing power. Okay, so the DFA, NFA, and epsilon NFA still only accepts regular languages. And as I've said, we'll show this in the next video. We will see that NFAs and epsilon NFAs can be converted to each other. So they are actually equivalent also. Also, please take note that even if a finite automaton looks deterministic because there's only uh, one, given one input, it transitions to one state. So it doesn't look non-deterministic because every input transition allows your state to transition to one state lang. But if there is epsilon transitions in your finite automaton, that automatically makes it non-deterministic. Okay, so even if, for example, all of your states, let's say Q, P, so all of them look deterministic, then on R, on B, so this looks deterministic, right? But for example, if it has an epsilon transition, even if it looks deterministic in this case, with this epsilon transition, that automatically makes it non-deterministic. Okay? Because epsilon transitions can only happen in non-deterministic finite automata. Okay? So, yeah. Okay, so that's epsilon NFA. And then finally, we will discuss something called the epsilon closure. Okay, so what is the epsilon closure? The epsilon closure of of state P is the set of states that you can reach from state P following only edges labeled epsilon, or meaning you follow only epsilon transitions. So what does that mean? So starting from state P, if you follow only if you only follow epsilon transitions, what are the set of states that you can reach, basically? So let's see example of that one. So what is the epsilon closure of A? Now from A, okay, let me, from A, there are no epsilon transitions, but you can stay in A, basically. So the epsilon closure of A is just A. And the reason for this is, at the very least, the epsilon closure of a state contains itself. Okay? So without epsilon transitions on epsilon, it will just stay in its own state. So epsilon closure of A is A. Okay? How about epsilon closure of E? So if we start here, so, well, the epsilon closure of E should have the state E itself, right? What else? It could also transition to B because of this epsilon transition, right? So it could go to B, and then it could also go to C because of this epsilon transition, right? Can we go anywhere else? We can, right? Because from B, if we follow another epsilon transition here, we can go to D. Okay? So from E, we can follow two epsilon transitions here, and we ended up in D. Okay? But from B, there are no other states that you can go to on epsilon. Same with C and D. So that's it. The epsilon closure of E is B, C, D, and E. Okay? So again, epsilon closure is the set of states that you can reach following only epsilon transitions. And at the very least, it should contain the state itself. Okay? So the next slides are just the explanation that I said. So epsilon closure of A is just set containing A because the closure of state contains at the very least itself. Epsilon closure of E is BCDE, as we saw, because E is the state itself, B and C because of the epsilon transitions from E, and then D was reachable from B with epsilon transition. So you have B, C, D, and E. Okay? Now, the epsilon closure of a set of states naman, so earlier we saw the epsilon closure of one state. How about epsilon closure of a set of states? So you just take the union of the epsilon closures of each state, basically. So if you want the epsilon closure of A, B, and C, then you just take the union of epsilon closures of A, epsilon closure of B, and epsilon closure of C. Okay, so just take their union. And for the extended transition function, the delta hat, it's the same. So it still maps the set of states Q and sigma star to the power set 2 raised to Q. So the delta hat QW is the set of states that are reachable from state Q following a path labeled W, right? So it's just like our NFA. So starting from Q, if you process W, what are the set of states that you can reach? However, the difference is that in the epsilon NFA, this path of processing W can include epsilon transitions. So that is the difference. So NFA, you are sure that all the uh, path symbols are from the input symbols. But in the epsilon NFA, the path processing the input string W could contain epsilon transitions because we allow this to happen. Okay, so so let's see this one. In the DFA and NFA, is there a difference between delta hat Q and string A versus delta of Q on input symbol A? So take note that we are processing only one a length 1 string here, which is A, versus the input symbol A. So in reality, there is no real difference. It's only a syntactic difference because this one is a string, this one is an input symbol. But really, the state or set of states that you get are the same, right? Because you are going to the same state or set of states here. However, in the epsilon NFA, will there be a difference between delta hat Q processing string A and just the delta of Q input symbol A? Well, there is, because this time they are not equal anymore. Why is that? Because processing the string A in epsilon NFA means that you're actually processing epsilon star A epsilon star, meaning there could be 0 or more epsilons along the way. Okay? So it could be that A lang siya, or pwede man na A epsilon epsilon, or pwede man epsilon A epsilon, or epsilon epsilon A, and so on. So you could attach 0 or more epsilons before and after your input symbol A. Okay? Whereas in the transition function, you don't really have the extra epsilons, right? So that's the difference. So in the normal transition function, delta of QA is just the set of states that you can transition to from state Q on input A. Okay? Set of states man siya. But in delta hat Q, processing string A, it's the union of the epsilon closures of each state in delta QA. So you still take the epsilon closures because you allow epsilon transitions even with a string A lang. Okay? So delta hat QA is actually the epsilon closure of the set of states that you can reach from Q on A. Okay? But in delta QA, you don't compute the epsilon closure because it's just the transition function. But here, it's extended. So since it's processing the string, then you need to take the epsilon closure. Okay, so let's see an example of that here. So what is the delta hat of A given input string epsilon? So since we're not processing anything, we can just take the epsilon closure of A, which is just A lang, right? So since you're not processing anything, you will stay in A, but you could still, there might be epsilon transitions, right? So what is the epsilon closure of A? And we said earlier that epsilon closure of A, oh shoot, epsilon closure, let me just move this one here. Of A is just A, right? Okay. Now, how about for this one? Delta hat A0. So A on a 0 will arrive in E, right? But from E, what is the epsilon closure of E? We have, from earlier, we said that it could go to, oh sorry, E, could go to B, C, D, and E, right? So it can go to B because of this epsilon transition. It can go to C because of this epsilon transition. It can go to D because of the two epsilon transitions here, and E because it's the actual state itself. So A on 0, although it only reaches E in the normal NFA, but since this is epsilon NFA, we can reach B, C, D as well, together with E. So that's B, C, D, E. Okay? How about the string A01? So first, let's process A0. If it's A0, we know that from the previous item, we could reach B, C, D, or E, right? So from these states, we only need to process ang 1, right? So process 1 here. From E, do you have 1? There's none. From B, do you have 1? Yes, there is. So you can go to C. From C, on 1, it goes to D. So this is the 1. And then on D, there's nothing. So from B, C, D, E, if you take 1, you can only go to C and D. Okay? But from C and D, we still need to take their epsilon closures because there could be epsilon transitions. But from C, there are no epsilon transitions. From D, there are no epsilon transitions. So we'll stay at C and D. Okay? So yeah. And then finally, for the last example, A on 1. So A, if it's just epsilon, it will stay in A. So we're confident that we're still in A. And then on 1, it goes to B, right? But we will take the epsilon closure of B because there could be epsilon transitions. And in fact, we could still go to D because of this epsilon transition here. So there are no other transitions, and then from D, you're also stuck because D has no transitions. So we're left with B and D only. Okay, so that is how you process your strings in the epsilon NFA. So you start with state epsilon. There could be epsilon closure of that state already. So for example, if you're starting at E, you're not really starting at E, you're starting at E, B, C, and D, because there are free transitions already from E to B, B to D, and E to C. So if you start at E, you're really starting at E, B, C, and D. So those are your starting states if you start at E because of the epsilon closure of E. Okay, so that's it. The next slides are again just explaining what I explained earlier. So delta hat of A on epsilon is just epsilon closure of A, which is only A because there are no epsilon transitions. So, and the closure of the state contains itself. For A on 0, we need the epsilon closure of E, so that is B, C, D, E. And the reason why it's E, it's because it's the only state that we can reach from A with 0 with this input symbol. Okay, and then on 0, 1, so from B, C, D, E, from A0, if we process 1, we get to C and D. So as I've said, A on 0 goes to B, C, D, E. From B, C, D, E, we can only reach C and D on a 1. So we'll take their epsilon closures as well. But the epsilon closures of C and D are still C and D because there are no epsilon transitions anymore. Okay, so and then in the final one, A on 1 is just epsilon closure of B, because you can only get to B from A on a 1. And then you can also reach D on from B on an epsilon transition, so you take the epsilon closure of B, which should be B and D. Okay, so A to D follows the path 1 epsilon through B. Okay, so those were the examples that I explained earlier. So lastly, the language of the epsilon NFA is just a set of strings that it accepts. And formally, the string W is accepted by the epsilon NFA if the delta hat of Q starting at the start state and you process the string contains at least one final state. But again, take note that in processing the string W, there could be extra epsilon transitions along the way. Okay, so you take a set of strings that if you use the delta hat starting from the start state, we process the string together with some 0 or more epsilon transitions that ends up in one of the final states. So intersection with final state is not empty. Okay, so yeah, so that's it. So to review, we discussed the non-deterministic finite automata, wherein from one state you're allowed to transition to a set of states. And we also discussed epsilon NFA, which allows you to transition even without taking an input symbol. So you're allowed epsilon transitions. We also discussed epsilon closure, which is the set of states that are reachable by following only epsilon transitions. Okay, so in this video we talked about non-deterministic finite automata, and it has the power of non-determinism. However, in our real-life computers, there is no non-determinism. So our real-life computers are deterministic. So how do we actually implement non-determinism in that case? So what is the purpose of having non-deterministic finite automata if we only have deterministic computers? So in our next topic, we will see how to convert a DFA to an NFA and vice versa. So they are equivalent. And we'll also see how to convert an NFA to an epsilon NFA and vice versa. So we'll also see that they're equivalent, and how to convert a finite automata to a regular expression and vice versa. Okay, so we'll see the equivalence of finite automata and regular expressions in the next video. Okay, so that's it for this video. I will see you next time.